Yeah, thank you very much all for coming. So tonight we have Maria Violaris giving a talk on quantum thought experiments. Maria is a PhD student at the University of Oxford, and she's researching the foundations of quantum information. Specifically, her DPhil research aims to reframe quantum thermodynamics using constructor theory. And she's also a passionate quantum communicator. She's the founder of the Oxford Quantum Information Society, winner of the FameLab 2020 competition, and is also a quantum community advocate at IBM. So yeah, we feel very lucky to have you here, Maria, and thank you again for agreeing to give this talk. So over to you. Thank you.
Well, thanks for the introduction, Mia. And yeah, thanks for inviting me to give the talk and for everyone for joining. I think it's a really cool organization, and it's really nice that you all have this network to learn about quantum stuff. Yeah, so today I'm going to talk about quantum thought experiments, which are related to what I'm researching. The things I'm going to talk about are kind of, yeah, the thought experiments that I think are most interesting in quantum physics. And I'll also talk a bit about how they link to some of my research interests as well. So just, yeah, to introduce myself and what my background is, I originally, well, I'm from Manchester. That's where I was when I was doing my A-levels. And then I went to Oxford to do physics undergrad. So I did a 4-year MPhys physics degree there. And then in my kind of 4th year project, so my last year of undergrad, I became interested in this theory of physics called Constructor Theory, which aims to kind of unify different aspects of physics. And I found that really interesting, and then ended up, well, it turned out that the people that kind of founded that theory were in Oxford, so I reached out to them and organised a project with them, specifically Chiara Marletto and David Deutsch, and then that led on to my PhD with the same research group in Oxford. So yeah, now I'm in 3rd year doing my PhD. And I've also done a few, had a few connections with quantum computing companies. I did an internship with a startup called Riverlane, which was trying to well, my internship was trying to build a Raspberry Pi quantum computing lab as a kind of simulation of a quantum computing lab. And then more recently, I've been working with IBM Quantum, mainly on this Quantum Paradoxes video series, which will include some of the, well, it does include and will include some of the thought experiments that I'm talking about today. And yeah, as Mia mentioned, I enjoy doing lots of science communication in general. And one of the things which some of you guys might be interested in is last year I organised a competition called Quantum on the Clock, which was about making 3-minute videos on any aspect of quantum science and technology aimed at A-level students. And hopefully that will run again this year. It's still in planning stages, but yeah, you might be interested in that. So yeah, now that we've had an intro, I'm interested to hear what the views of people here are on thought experiments. So could you just, I think there's a raise hand function. Could you just raise hand if you have heard of thought experiments before? So you've heard the idea of thought experiments being used in physics. Cool. So we have quite a few raised hands. Cool. Yeah, so just to kind of, yeah, thanks for raising the hands. You can put it down now if you want. And yeah, so in case you haven't heard of quantum thought experiments of thought experiments in physics or science in general, the general idea of thought experiments is that instead of going into a lab and trying to do an experiment, or the way you might do in one of your labs at school, the idea is to do an experiment conceptually. And so just to think about what would happen if this, and this happened, and then to work out the consequences. And so essentially these are like, thought experiments are like a story that you think about how something could happen. And then it's really amazing how just thinking about what might happen in different situations can lead to really big breakthroughs in science and technology. So one of the most famous people for using thought experiments in science research is Albert Einstein. He has lots of famous thought experiments to do with that led him to discover like special relativity, for example, by thinking about what would happen if you were riding on a photon at the speed of light and these kinds of things. And that's just one example from loads of examples in science where thought experiments have led to like a new breakthrough, from pointing out some contradiction or something that doesn't make sense with what we know at the moment. So that's why I think thought experiments are a really cool tool, because we can like make new discoveries without even needing to step into a lab. And in particular, there have been some really cool insights into quantum physics that have come from thought experiments. So the ones that I'm going to focus on today, first I'm going to introduce a thought experiment called the quantum bomb tester, which is, it shows some really weird aspects of quantum physics. Then I'm going to talk about a thought experiment which I refer to as the quantum AI thought experiment, and something which like surprisingly few people know is that this thought experiment actually led to, or was pretty important in the discovery of the quantum computer, in coming up with the idea of what a quantum computer is. So I think that's a really cool one to know about. And then I'll talk a bit about using thought experiments to understand the arrow of time, why it feels like time moves forwards and not backwards, in particular applied to knowing that, to the laws of quantum physics. And that links a bit to my research. And then at the end, I'll explain another thought experiment to do with testing whether gravity has quantum features, which is one of the kind of biggest mysteries of physics at the moment. And it is, I think of it as a kind of thought experiment of the future, because it kind of goes beyond thinking about thought experiments in quantum mechanics and trying to think even beyond that into like a future theory that solves problems that we have right now. Cool. So I'll get started with the quantum bomb tester. So yeah, there's a quote from, so there's a scientist called David Deutsch, who's the one that came up with the quantum AI thought experiment that I'll talk about in a bit. But yeah, when I was discussing the quantum bomb tester thought experiment with him at one point, he described it as one of the weirdest things known to science, which is pretty cool. So this was a thought experiment that two scientists, Avshalom Elitzer and Lev Weidman, came up with. And I'll give a summary of it here. So the idea of this thought experiment is that you imagine that you are given a box and you can't see what's inside. So let's say this is the box. It's actually the box of a chocolate orange, but you're either told that there's a bomb inside the box or not. So there's either a chocolate orange inside here or not. The chocolate orange is my analogy for the bomb. And your challenge is to figure out whether or not there is a bomb inside the box without setting off the bomb. Now, the twist in this thought experiment is that the bomb is really, really sensitive. So even like a single particle interacting with the bomb will cause it to explode. So if I'm trying to work out whether there's a bomb in this box and I try and like probe it with a single particle to check if it kind of bounces back or not, then that will explode the bomb if it's there. So classically, using just normal classical physics, there's no way for us to work out whether or not there is a bomb in the box without exploding the bomb. And what Qsium, what Elitzer and Weidmann came up with is a way of being able to work out whether or not there's a bomb in the box using quantum physics. So the idea is that we have this component here, which is called a beam splitter. So this is like it's like a mirror, but half silvered. And what this means is that here we have a single photon, so a single particle of light. And when we fire it at the beam splitter, it has it goes into a superposition of being reflected from the beam splitter and transmitted straight through. And so the beam splitter has this ability to put a photon, a single particle, into a superposition of two paths. And then what we have at either end are two mirrors. So they just reflect the photon, so they reflect each part of its superposition. And then we make these parts of the superposition meet again at another beam splitter. Now, because of the wave-like properties of quantum systems, at the second beam splitter, the photon interferes with the other parts of its superposition, making like constructive interference, like in a similar way to how you can have constructive interference with like water waves, for example. And then it actually merges the two parts of the superposition back into a single photon that comes out of the second beam splitter. So that's what happens in this setup, which we normally refer to as an interferometer. And what Elitzer and Weidmann suggested is, what if we put our bomb into the interferometer, and then when the photon interacts with the bomb, it will cause the photon's state to be projected into one of these two paths that the photon could have gone in. So into either the top path or the bottom path. Some people refer to this as collapse. Some people don't like to use that terminology. I'll talk a bit about that later. But yeah, there'll be a 50% chance that the photon is projected into the top path, 50% that it's projected into the bottom path. And if it's projected into the bottom path, then it will interact with the bomb and cause it to explode if the bomb's there, which is not what we want. But if instead it actually collapses into, or is projected into the top path instead, then when it reaches the second beam splitter, it'll be evenly split again into a superposition of the being reflected and transmitted. And then we have these detectors at the other end, which will detect. So again, when we have a detector, the photon will be projected into either the reflected or transmitted path. And so there's a 50% chance of getting the detection at each of these detectors. So in the case where the photon is projected into the top path, and then the photon is detected in this top detector, then what we've achieved is that we've managed to work out that the bomb is there without setting off the bomb, without it exploding. Because if the bomb wasn't there, then only the transmitted detector would go off every time we do this experiment. But if the bomb is there, then it can cause the photon to be detected in the top detector, even though the photon kind of hasn't interacted with the bomb. So this is the kind of the really amazing outcome of this experiment is that of this thought experiment is that you can detect a bomb without interacting with it. And this is known as interaction-free measurement. So so that's the Elitzer Weidman bomb tester. And after this thought experiment was proposed, it's then been kind of experimentally implemented, not exactly with bombs or chocolate oranges, but with having like an atom, for example, in place of the bomb, and then running this experiment, and it all checks out. It actually works. And some people have found applications for this, for example, trying to use it to image delicate objects, for example, so that you can image them without destroying them. Yeah, and maybe another thing to mention is that the people that proposed this thought experiment, or Lev Weidman at least, and if you look at the original paper proposing it, then you'll see this. He sees this thought experiment as demonstrating what's called the many worlds interpretation of quantum mechanics. So what he says is basically, if the photon really is just projected into either this bottom path or this top path, and somehow when it's projected into the top path, it hasn't interacted with the bomb, then that's a paradox. Like, you can't have something affecting something if it's never actually interacted with it. So then what he says is, well, actually, the photon must have gone down both these paths, but in parallel universes. And even though it didn't interact with the bomb in one of the paths, in one of these universes, it did interact with the bomb in another one of these universes. And so that resolves the paradox, because the photon still interacted with the bomb. So not everyone agrees with this view, but it's interesting that that's how it was proposed in the first place. So yeah, I'm just checking the chat for questions. There's one of why this would work only 50% of the time. So yeah, so this experiment, as I've shown you, would only work like 25% of the time when there is a bomb there, because 50% of the time it will explode the bomb. And then of the other 50%, half the time it'll give an inconclusive result, because it'll be in the detector that it could have been in without the bomb. And half of that time we'll get the result we want. So there's a 25% success rate. But there's actually a variation of this thought experiment, which people worked out later, where you can basically like chain together lots of these beam splitters and kind of send the photon round and round and round through this setup in such a way that you can work out whether or not there's a bomb there with up to 100% accuracy. So as high probability as you want of having a successful detection, there's a way of doing that by adding more and more beam splitters. In the no bomb scenario, why does only one detector detect, and why is it always the same detector? So yeah, so in the no bomb scenario, the effect that's causing only one detector to detect is the fact that single photons are able to interfere with themselves, so that a photon can split into a superposition, and then these parts of the superposition can then interfere with themselves to merge back into a single photon. So if you've kind of started looking at some quantum computing stuff, and maybe the kind of quantum computing way of phrasing this would be that we have a qubit that begins as a 0, and then we have the beam splitters acting like a quantum gate, which puts it into a superposition of 0 and 1. So for example, there's a state called the plus state, which is like 0 plus 1, which a quantum gate called the Hadamard gate can transform a qubit into. And then if you apply another one of these gates, so another Hadamard gate, then it'll take it back to a 0. So it'll take the superposition of 0, 1 back to 0. So that's the kind of quantum computing version of why you go from how you can go from a fixed just having one path to two paths to just one path again. And yeah, it's the same effect that causes interesting things to happen in the double slit experiment, if which you may have heard of. Cool. So are there any other questions anyone wants to ask about the bomb tester before I move on? Okay. I think we're good to move on then. Yeah, thanks for the questions, by the way. Please keep putting them in, because yeah, it's good to keep this as interactive as possible. Yeah, so that's the bomb tester. So now I want to talk a bit, so linking with this idea of whether the photon actually collapses into one state when it interacts with the bomb, or whether it actually goes into multiple states when it interacts with the bomb. This is a kind of big question that lots of people have been debating and discussing in quantum physics kind of ever since Schrödinger's cat was thought of. And then there's an interesting thought experiment that was proposed by David Deutsch, which provides a way of testing out whether collapse happens, so whether this irreversible collapse happens when you interact with a quantum system or when you measure a quantum system. So this is kind of like the idea of, so there's the problem of Schrödinger's cat, of can a cat be dead and alive at the same time? How does it collapse into one state when we look at it? Is there any way we could ever test this? And this thought experiment provides a way to test this. So can I just have a show of hands of how many people are familiar with the term qubit, or I kind of feel comfortable with the term qubit? Okay, quite a lot. Cool. Okay, so quite a lot, maybe not quite everyone, but yeah, cool. Thanks. Yeah, you can put the hand down if you want. Yeah, so just to summarize, so normally in computing, we're familiar with bits, which can be in the state 0 or 1. And that's what all classical computers are based on, processing bits which can be zeros and ones and flipping them between 0 and 1 and 1 to 0, like the two sides of a coin. A quantum bit, or a qubit, can also be in the 0 state and 1 state, but it can also be in a combination of 0 and 1, which is known as a superposition state. And if we apply quantum mechanics to observers and people that are to our measuring instruments and to whatever detectors we're using, then what it says is that when I measure a qubit, a quantum bit, then I become entangled with it, quantum entangled with it. So that means that when I measure a qubit, we kind of split into these two. We become a joint superposition state, me and the qubit, where one version of me sees the qubit saying 0, and another version of me sees the qubit saying 1. And so that's this kind of many worlds idea, which happens when we apply quantum mechanics to all levels, including detectors and observers and so on, which not everyone agrees with, but that's the consequence of doing that. And some people think that is very strange and maybe shouldn't be possible for there to be multiple versions of you seeing different things, and that what must actually be happening is that when you see the qubit, it collapses into the 0 or 1 state with some probability, and that we don't actually become entangled with it. And the whole point of what this thought experiment is testing is to test whether an observer looking at a qubit causes it to have an irreversible collapse, or whether it actually becomes entangled, and so that interaction can, in principle, theoretically, in a thought experiment, be reversed. So we're testing whether measurement can be reversed or not, measurement of a qubit. So I thought it would be fun to see if we can implement a version of this, or a kind of version of this thought experiment ourselves. So is there anyone that would be is there anyone that would be willing to volunteer for the thought experiment, especially if if anyone has a coin to hand, that would be really useful. But I need two volunteers if people would like to. So yeah, we have 2 raised hands, Zach and Samuel. Thanks. So yeah, thanks for volunteering. Does one of you have a coin?
I thought I did, but it's white on both sides.
I have a coin.
Yeah.
Yeah. Okay.
Yeah.
Thanks. So is there a way of making your coin like asymmetrical, Zach, having 2 different sides?
Yeah, I could draw a dot on it.
Okay. Thanks. Cool. So in our thought experiment, would you mind keeping your hands raised, the 2 volunteers, Zach and so it's just the videos then drop off my screen when the Samuel. Yeah, thanks. Cool. So so one of you will be, so what we're going to imagine is that we can simulate an observer on a computer, and Zach with the coin is going to be the observed, is going to be the simulated observer, and Samuel is the person controlling the computer. And so so we're imagining that Zach has that Samuel is simulating Zach on a computer with access to a qubit that's in superposition. Now, can we use the Zoom chat? So so what we need is for Samuel to ask Zach to measure his qubit. So we're going to use the coin as like a simulation of the qubit. So Samuel, would you mind putting in could you put in the chat, could you put a question for Zach or an instruction of, please, can you measure your qubit? So that's what you're trying to, this is the programming of the simulation. Great, thanks. And now, Zach, please can you flip the coin and decide, decide one side being 0 and one side being 1, and flip the coin and then tell us in the chat when you've made your measurement. Just tell us that, just confirm that you've measured your qubit, but don't tell us what you got. So don't tell us whether it was heads or tails. Cool, thanks. So now, now what's going to happen is Samuel, who's controlling the quantum computer, is going to try and reverse Zach's measurement of the qubit. So Samuel, could you put an instruction in the chat to Zach to flip the coin again? And then Zach, can you follow the instruction in the chat? And so by flipping the coin, you're doing the reverse of the measurement. So just to recap, so thanks Zach and Samuel for doing that. So to explain what's happened here is that Samuel simulated Zach of measuring this qubit in a superposition. Zach saw either 0 or 1, but didn't tell us what he saw. And then Samuel reversed Zach's measurement. So if Zach as an observer can truly be described by quantum mechanics, then everything to do with that measurement was reversible, and so it was all reversed, and the qubit went back into a superposition of 0 and 1 when it was reversed. But if there was actually a collapse, was an irreversible collapse happened when Zach did his measurement, then the qubit actually won't return to a superposition of 0 and 1, and it actually just stays as 0 or stays as 1, depending on what Zach got. But we know for sure that the qubit was definitely measured. So because we've got this information in the chat, we know that Zach measured the qubit. So what that means is that we can now, so what Samuel can now do is measure whether or not Zach's qubit has returned to a superposition or not. And that measurement will, so in practice, you have to run this experiment lots of times. And if it does return to a superposition, then when you make your measurement of whether it's returned to a superposition, you'll keep getting the same answer of yes, it's returned to the right superposition. And if it didn't, if it collapsed, then you'll be getting an answer that kind of flips between two possibilities. So it'll be kind of half filled with one answer and half filled with another outcome. So that's, I won't go into the details of why exactly it happens that way. But the main kind of result of doing this is that by attempting to reverse Zach's measurement of the qubit and then checking if it returned to a superposition or not, we can actually check whether an irreversible collapse happened. And it's important that we never found out that information about whether Zach got heads or tails, because that would have put us into the superposition as well. We'd have become entangled with that coin and then, or that qubit, and we wouldn't be able to then reverse all that without reversing our own memory of what had happened as well. But with this technique, we can actually reverse that. And so that's the idea of this thought experiment, was to test collapse theories versus no collapse theories. To actually implement it, we would need to be able to simulate an observer on a computer and simulate their interaction with a quantum system. And the person that came up with this thought experiment, David Deutsch, kind of realized this. And even though he didn't call it a quantum computer, it was the idea is that this simulated observer interacting with the qubit would actually need to be implemented on a quantum computer to be able to do this thought experiment. You'd have to actually have your computer made out of qubits to be able to do this simulation in the first place. And that was an important factor in his later discoveries in kind of being at the beginning of the field of quantum computing, which he did some major initial contributions to. So that's what I refer to as the quantum AI thought experiment. And thanks, Zach and Samuel, for being really great volunteers on being the observer and the simulation. Are there any questions about this thought experiment? Though we have a question about the collapse theory. Is the collapse theory personal? If someone other than you experiences wave function collapse, do you also experience the wave function collapsing? Yeah, so I think it's personal in the sense that, so the way I think of it is kind of like, it's kind of like the, well, yeah, okay. I guess if the collapse theory in the sense of irreversible collapse, the people that think that a quantum measurement causes an irreversible collapse think that everyone, so let's say that I have a friend of mine measures a qubit. If I'm a collapse person, I'd say when my friend measures the qubit, they've collapsed the qubit state and it's collapsed for all of us. If I'm a non-collapse person, then what I'll say is when my friend measures a qubit, my friend became entangled with the qubit. In theory, I could reverse that interaction between my friend and the qubit if I had enough control over them, but I don't, and it's very unrealistic to have that. And then when I measure my friend, or when I ask my friend what result my friend got, then I become entangled with my friend and the qubit, and then I just see one outcome. And does this play into the idea about how consciousness could have a quantum element? yeah, this is interesting. So this thought experiment that I just briefly mentioned of having a friend that measures a qubit, so it's the kind of simpler version of this quantum AI one, is called Wigner's friend. It was proposed by Eugene Wigner, who was a Nobel laureate in like 1961 or something. And he actually proposed a theory to explain collapse in terms of consciousness. Like he thought that consciousness was important in that. I think at the moment, no one really thinks that consciousness is important for that consciousness is like the reason behind collapse. There are various theories about, for example, some people think that gravity causes collapse. Some people think that an object of a certain size or complexity or mass should collapse. There's a kind of range of theories called objective collapse theories, but I don't know of a kind of well worked out one. Well, yeah, to be honest, none of them are kind of fully worked out, in that that's why there isn't a collapse theory that's been fully worked out. But yeah, I don't think that there's any kind of main ones. Like maybe some people still kind of look into the idea out of interest, but I don't think there's a main, there's a lot of people that think that consciousness causes collapse. There is some work that people like Roger Penrose are interested in looking at whether quantum effects have a role in consciousness, which, there's kind of other ways that quantum effects could have a role in consciousness. For example, there's a field of quantum biology of seeing if quantum effects affect biological systems in an interesting way. And there are some speculations that some parts of the brain could possibly take into account quantum effects in the way that they work. It's very speculative research. It's cool stuff, but we'll see what happens with that. The question of, has any of this been experimentally tested, and is there any effort being made to do so? So the way I think of this thought experiment of like trying to have an observer detect a qubit and then undo it, experimentally testing this depends on like what you count as an observer or what you count as a detector. So if what you count as a detector is something that is kind of as big as a molecule, for example, then people have already done experiments where they've let molecules interact with quantum objects and then reverse them. So in that sense, the experiment has been done and verified that quantum mechanics does apply to objects as large as molecules, detectors as large as molecules in that sense. And so then there's this kind of attempt to try and push that boundary further and further and further, which kind of rules out more and more collapse theories if it keeps going. So the kind of the full version of really trying to simulate an observer and be able to reverse their interaction with a qubit, that would need like us to be able to implement an artificial general intelligence, basically, like to be able to simulate a version of something that's just as much an observer as me and you. So that's kind of I reckon is pretty far into the future if we ever get to that point. And then there's this spectrum of trying to like push the boundary to rule out more and more collapse theories as we put more and more big and complex detectors or observers into this experiment. So there's another question: if gravity causes collapse, how can the probabilistic nature of quantum mechanics work near black holes? I don't know what the gravity causing collapse theory would, what its implications are near near black holes, but yeah, it's an interesting question. I'll see if I think of a good answer to that. I'll let you know. Cool. Yeah, does anyone have any other questions about this thought experiment? Yay. Would an AGI be necessary? Naively, could you stick a sensor onto a quantum object, log the result, then wipe the data, therefore resetting the system? Yeah, so this kind of yeah, so the important thing with this experiment, yeah, so you can do this experiment of having a detector interact with a qubit and then reversing it without it needing to be a simulation. So the idea of bringing the simulation in there is for if we wanted to do it with a human-like observer, of trying to get a consciousness of some sort, then the easiest way to control that would be to simulate it on a quantum computer, and then we like apply all the reverse gates to undo it and stuff. But yeah, if you want to do it with another kind of object or whatever you class as a detector, then you can do it kind of physically without simulating it. But yeah, it's just a question of you have to be able to have quantum control over whatever object you're doing it with. That becomes really difficult the bigger and more complicated the object is. That's why building quantum computers is really hard, because as we try and add more and more qubits, then we have more and more unwanted interactions from the environment, and it makes it a lot harder to control them. But yeah, there's lots of progress being made on pushing out that boundary. Cool. So as the kind of the last the last main thought experiment I wanted to mention is about the arrow of time. So could I just do another show of hands? Can you put your hand up, raise hand if you've ever scrambled an egg? So like you do for cooking, make a cake or a pancake or an omelette or anything. Cool, lots of raised hands, which is good. Yeah, we've all been busy baking and cooking and things. Cool, great, thanks. Yeah, you can put down the hands now. Thanks. So now I have another question of can you raise your hand if you have ever unscrambled an egg? So you've scrambled an egg for so long that it's gone back to being a yolk and a white. Has anyone unscrambled an egg? Okay, I'm not seeing any hands. Oh, Ryan, did you? No. Okay. We don't have anyone who's unscrambled an egg. Okay, so that's what I would have expected, because if you think about what happens when you scramble an egg, so it begins as a yolk and a white. So you've got lots of yolk particles in the yellow bit, and then lots of white particles. And as you mix it together, then all of the particles end up mixed up. And if you just think about the kind of the probabilities of how the particles are likely to end up, there's lots more ways for the egg particles to be arranged for it to be mixed together. So for it to be in one of these scrambled states, than for it to be separated in a yolk and a white. It's very unlikely for an egg to be split into, for the particles to be, say that all the yolk particles are gathered in one place and all the white particles are gathered somewhere else. That's a much smaller proportion of all the ways that the egg particles could be arranged. And so in physics terms, we say that the yolk and the white are in a very ordered state, and the scrambled egg is in a very disordered state. and we quantify how ordered something is using a quantity called entropy. And I think, unfortunately, entropy only comes into high school syllabuses in a few kind of random, well, I don't know. I think it comes into some chemistry syllabuses, but it isn't really referred to in physics, which is a shame, because I think it's really interesting, because it's what a lot of physicists use to define the arrow of time. So they say that the entropy of an isolated system is very unlikely to decrease. So it's very unlikely for a system to go from disorder back to order. So with the egg, it's very unlikely for it to go from being mixed together to being a yolk and a white. But, and this is called the second law of thermodynamics. There's loads of quotes about how this is like really, really fundamental and important, and that other laws of physics may come and go, but like the second law is one that there isn't really any way around it, a lot of people say. And and this is used to define the arrow of time in things being irreversible, going from order to disorder. But interestingly, for such a fundamental law, there's a lot of issues with it. So firstly, there's this statistical aspect of all it says is that things will probably go from order to disorder, but it doesn't really tell you whether they'll exactly go to disorder or not. And it's pretty strange to have a statistical law of physics. So other laws of physics, like the conservation of energy, for example, are precise and exact, and they don't depend on probabilities. Another weird thing is that if you go to a kind of small scale, or imagine you just have a few yolk particles, then it could actually go from a yolk and a white back to from being mixed together back to a yolk and a white if there's just a few particles. And interestingly, in quantum mechanics, we know that our underlying laws of quantum physics are all reversible. So every quantum interaction that's allowed by quantum physics, the reverse interaction is also allowed. So if you zoom into a system close enough and look at its quantum interactions, and then look at the reverse quantum interactions, both ways are perfectly allowed by the laws of quantum physics. So there's a kind of strange problem here in that we have this symmetry in the underlying laws of quantum physics, but then we have this statistical probabilistic second law showing the arrow of time that emerges on large scales. And what I interested in and have been looking at in my research as well is a different approach to this problem. So instead of saying that an egg is very unlikely to go back into a yolk and a white, we phrase the problem in a different way. We say, and this is the way that this law was first come up with, it wasn't in the statistical way, it was in this other approach, which is to say that there exists a reliable way of scrambling eggs, but there's no reliable way of unscrambling eggs. And so a reliable way of scrambling eggs is, for example, to use a whisk, and a whisk can be reused to scramble an egg over and over again, and it retains its ability to scramble an egg over and over again. So it's like a catalyst for scrambling an egg. Whereas there's no whisk for unscrambling an egg. If you want to unscramble an egg, you'll have to put in loads of resources to find some way of unscrambling it, and you won't be able to do that in a reliable, repeatable way. And by saying that scrambling an egg is possible and unscrambling an egg is impossible, we have a way of framing a type of irreversibility in an exact way. We haven't said any probabilities in our statements, and so we've managed to kind of avoid the probabilities aspect. And then there's this question of, well, can we actually apply this to quantum physics? Is this true for quantum systems? And what I've been looking at in my work is thinking about a version of this where instead of having a yolk and a white and a scrambled egg, we think about qubits, and there's different types of states that qubits can be in. There's pure states, which are like low entropy, like the ordered egg, the yolk and the white. And then there's mixed states, which are high entropy, like the disordered scrambled egg. And then I've been looking at what I call like a quantum whisk, which is, it kind of does what a whisk does for a normal egg. But in my case, it transforms a qubit from a pure state to being approximately in a mixed state. And it can do that again and again and again. And then I've been showing that if we try and use the same quantum whisk to do the reverse task over and over again of purifying the qubit, then it won't work. It'll kind of deteriorate over time. So we're trying to show that this exact form of irreversibility can actually apply to quantum systems, even though all of the laws of physics there are reversible with time and the underlying laws of physics. So that's a summary of the ideas about the arrow of time. And just to kind of wrap up, because we've been talking a while, I will share screen again. I'll look up this. Cool. So let me go on slideshow. Let's go to this slide. Okay. So this idea that I've just talked to you about of reframing the second law in terms of what's possible and impossible in a cycle is so that's the idea behind this theory I mentioned earlier, constructor theory. The aim is to express the laws of physics in terms of what's possible and impossible. And another kind of consequence of this way of expressing the laws of physics is that we can make laws about we can conjecture laws about what's possible and impossible without needing to commit to the specific kind of the specific laws of quantum mechanics, for example. So we can say principles about what we expect to be possible and impossible, even for like a future theory of quantum gravity that combines quantum mechanics with general relativity. We don't know what the dynamics of that, we don't know what that theory will look like yet, but we still expect it to obey the conservation of energy. We still expect it to obey these laws of thermodynamics. And so we can draw some conclusions about these future theories without actually needing to know what they are yet. And a really cool example of that with another thought experiment was recently proposed by my supervisors, Qsium, Vlatko Vedral, a few years ago. Came up with this thought experiment to test the non-classical features of quantum gravity. So the idea is there's a future theory, we don't know what it looks like, but we can still test whether it has some quantum-like features, even though we don't know exactly how to describe it. And so this is a figure from a paper about this test. And you'll see it looks very similar to this bomb tester experiment that I told you about earlier. It's again using an interferometer with these beam splitters and mirrors. But instead of a photon, here we have a mass, and we're putting a mass into superposition. So you can see we have this mass. We use the beam splitter to put it in a superposition of being in two different paths. And because these are different paths in space, they will each, if the gravitational field has quantum properties, so if gravity behaves in a quantum way, then the gravitational field will also be in a superposition of being centered in these two different positions. And then there's an experiment we can do by bringing in another mass to basically see if that mass enters this superposition by interacting with the gravitational field. So the gravity is like a mediator. It's like an in-between thing between these masses, and we check if putting one mass into a superposition leads the other mass to be in superposition. And if it's a yes, if gravity is able to cause this superposition in the other mass, then we know that gravity has some non-classical features, even though we don't know exactly which theory fully describes it. We can rule out, we can kind of decide between, does it have classical features or does it have quantum features? And the way that this thought experiment, so these principles about what's possible and impossible that I spoke about led to this thought experiment, in that these conclusions come from assuming some of these principles that don't depend on the specific theory of quantum gravity that you want to use, but just using these principles leads you to this conclusion without having to commit to that theory. So that's the kind of the thought experiment that I wanted to end on, because it gives kind of hints of how we can construct thought experiments in the future based on these ideas. Just before finishing, if you're interested in some of the things I mentioned, I can send around these slides later, which have some links to the Quantum Paradoxes series. I've made 5 videos for it already. There's 8 more coming up, which should be fun. You can subscribe to the Qiskit channel if you're interested in those. And if you're interested in the quantum thermodynamics stuff that I talked about, the kind of arrow of time ideas, I did a 20-minute flash talk on this, which is kind of accessible if you're interested in that. And yeah, I'm on LinkedIn or Twitter if you want to connect on there. And yeah, I just included some other resources on quantum information, which you may know already, but if you don't, there's the Qiskit YouTube channel, Qiskit textbook, and yeah, various other resources and interesting popular science books to learn about these kinds of ideas. Cool, so I will finish there, and I'm happy to take questions. I think there's some in the chat already. Yeah, shall I go ahead and answer the ones in the chat? If yeah.
Just to say thank you very much for the talk. It was really interesting, and I'm sure everyone's really enjoyed it. So thank you. Yeah, it's been great.